Physics is understanding how the world around us works. And that means distilling things down to their simplest principle, the essence of what is happening in there. What then derives from that is maybe a model that explains it, or it might actually be a mathematical equation. And then applying those models and equations is what the physicist does. If we're looking at how things work, we can break that into a number of different sections. How forces affect the motion of objects, we call it mechanics, is a foundational bit for physics. But we also might look at how electricity is carried through materials, and also how that interconnects with magnetism. There's also the study of thermodynamics. That's how heat can be absorbed and released by substances. When we move into Unit 3 and 4, we extend those ideas and look at more complex movement and mechanics. And then the more exotic and fanciful things, the Einstein ideas, that is relativity, or how the quantum world works. So when we're explaining a physical principle, almost always, if we can't bring it down to a mathematical formula, then we can't actually explain it in its purest form. So it's important to recognise that maths will form an integral part of the solution to so many problems in physics. However, the actual level of maths that's needed is really not particularly advanced. But a physicist needs to concentrate on the physics they're thinking about, and therefore the fluency in their mathematical techniques is really a great asset, so that you can spend your time concentrating on physics and let the maths solutions take care of themselves. To understand a principle, without a doubt, a demonstration, something practical, has to enhance and illustrate that idea. And also when a student does understand, it's really crucial they can investigate. So it's a component of both Year 11 and Year 12 of physics that students design their own investigations to explore the variation of different factors around a law or principle that they might be looking at. An example of how that practical work may well influence our understanding, let's look at radioactivity. So we might have some samples that we're going to show the core types of radioactivity. These will be stored in a safe way. There is real strict regulations about how we can use and manage those substances, and we test those out. We test them in a controlled way. But then we go to our natural substances, a piece of granite. And that piece of granite also has the very same reactivity that we have in our controlled samples. So the students get to see and compare their real world does actually relate back to the theoretical models that we deal with. It goes without saying, if we're explaining how the world works in physics, then of course it's relevant to that world around. Quite often the challenge in that real world is to try and distill what that simple idea is and detach it from the complexity of our world. For many physics students, engineering is the natural pathway that they've been looking for. And of course that is very relevant, but physics actually underpins so many other areas in tertiary education. In the areas of physiotherapy or prosthetics and orthotics, an understanding of what we call biomechanics, that's basically the physics of the body, is foundational. But you can also look at those emerging technologies, the environmental engineering, how we're going to find new ways of harnessing energy and making it sustainable. I think probably the most relevant thing to mention in terms of careers in physics is because physics is foundational in so many courses, what people quite often say at college is, oh, I wish I'd studied physics at school, because that's what you have to do when you get to college, to have those basic understandings for the principles that will underpin your chosen career or pathway.